Hey everyone, I'm goGuild, machine learning engineer at GoML. Today, I'm showing you our AI-powered video generation and talking of that system. Basically, the whole journey from R&D through model training all the way to production. We will hit the architecture, the avatar pipeline, and scaling it up. So let's get started. Our work was driven by two real claim challenges. First one, a personalized learning and job application platform, which requires AI generated video content at scale. They needed enhanced engagement, accelerated skill development, improved placement rates, and consistent quality across thousands of users. So second one is complete opposite of first, a virtual activity host for senior communities. This required a realistic avatar running interactive sessions. Key requirements includes natural human appearance, personalized content per community, CRM integration, and real-time responsiveness for natural interaction. Two different problems, both demanding realistic avatars and quality, but with very different technical constraints. This diversity shaped our entire R&D approach. Initially, we started with ready-to-play avatars. These avatars were quick to implement and web-friendly, but we hit a critical problem there. They looked too cartoonish, so the client rejected them. So we used character creator 5 avatars. These avatars were photorealistic, highly detailed characters running in a web browser. This was a quality leap our client needed. And let me break down the architecture here. So the user input comes from the chatbot UI. A user types a question or a message. Python backend handles inference orchestration. It receives the input and coordinates all the processing. Next is TTS engine, which is text to speech engine, converts that text into speech, generating the audio dialogue that our avatar will speak. Next is lip sync. For lip sync, we use Rhubarb library, which generates precise mouth cue timings. These are called bisames on the server side. This is critical. Rhubarb analyzes the audio and produces timing data that tell us exactly which mouth shape to display at each millisecond. Next is 3.js runtime. We render the 3D model using 3.js. It receives these cues and maps them to CC5 blend shapes in real time, creating perfectly synchronized lip movements in the browser. Rhubarb generates these precise Visames timings server side, and those cues are then mapped to character creator 5 blend shapes in real time within 3.js. Our modular architecture supports both CC5 for realistic avatars and ReadyPlayer.me for stylish ones. We can switch between them based on client's needs. We have also optimized asset loading and shader effects for the browser rendering performance because these high quality avatars need to run smoothly even on the standard hardware. So in this next demo video, you will see the complete pipeline working from user input all the way through to the animated avatar speaking with perfect lip sync.
Welcome to Connect Care. I'm here to help you every step of the way. Whether you have questions, need support, or just want quick guidance, how can I assist you today?
We conducted a systematic evaluation comparing commercial APIs against open source models. Let's start with the commercial options. Hagen was extremely attractive, high quality output and easy API integration. But here is a deal breaker. Price ranges from $30 to $100 per minute of the generated videos. For production use at scale, this becomes cost prohibitive. Imagine generating hundreds or thousands of videos for a personalized learning platform. The cost would be astronomical. So DID next offered a good lip sync quality, which was promising. However, their pricing structure and rate limits would block the production use. We needed something we could scale without hitting API quotas or burning through budgets. On the open source side, we evaluated three major contenders. Ecomimic. Ecomimic showed limited identity consistency. The avatar's appearance would shift based on generation. We also encountered artifacts on fine facial details, which hurt the realism we were targeting. Next is Satoka. Satoka had visible jitter on long form sequence. The temporal coherence, how smoothly the motion flows from frame to frame, was weak. For videos longer than few seconds, this became really noticeable. Next is 1 to GB models. It produced most visually consistent results across our entire test corpus. The lip sync accuracy was excellent. The identity remained stable, and overall quality was comparable to commercial solutions. 1 2GB produce the most visually consistent results. However, this is important. There is trade-off. Inference latency is higher, which makes it unacceptable for real-time use cases where you need instant response. Let me show you a 1 2GB in action. What's the facial consistency and the lip sync precisions and natural motions?
Front-end engineering aligns well with the candidate's existing skills in Microsoft Excel, management, and problem solving. These skills translate effectively to front-end development, where data manipulation, project management, and creative problem solving are crucial. The candidate's experience with user research at Anudio, while listed as a missing skill, actually provides valuable insight into user needs and behaviors.
Hey everyone, Gayatri here. So I'll speak about model fine-tuning and optimization we did to meet the requirements of the use case with the WAN 2GB model. Let me go into the model architecture. So we are working with the WAN 2.2 I2V A14 billion parameter model. So I2V is nothing but image to video. The key distinction is that this is a native 3D diffusion transformer. Now, most video models take a 2D image diffusion model and bolt on temporal attention layers, while WAN 2.2 was designed from scratch for spatio-temporal generation. So now coming to the four components. The first is the UMT5 text encoder, a heavily parameterized encoder extracting dense semantic pairs. This conditions the generation of text descriptions at a deeper level. Second is the casual 3D VAE, variation autoencoders. So traditional VAEs compress spatially, but in this model, VAEs compresses across spatial and temporal dimensions simultaneously, which dramatically reduces latent space dimensionality, which is essential for making 60-second generation tractable. Third is the 36 channel input tensor. So we concatenate 16 channels for noisy latents, 4 channels for binary mask, and 16 for the repeated condition image latents. Now through this, the identity is baked into every denoising step. Lastly, the training objective. So wave prediction training objective makes um, basically optimizes the velocity vector rather than just predicting noise. So this results in faster convergence for high resolution video dynamics. Now imagine fine-tuning a 14 billion parameter model. It's not just a machine learning problem, it's an infrastructure engineering problem. So we faced three critical challenges. The first one was the VRAM wall. We're using rank 128 LoRa, targeting Q, K, V, and output projection matrices in the diffusion transformer attention blocks. Even with PEFT, optimized states for 14 billion parameters resulted in out of memory on an 8 GPU cluster. So we solved this using deep speed zero stage 3 with CPU offloading, which sharded optimizes states, gradients, and parameters across all distributed ranks. The second one is the input output death spiral. When deep speed aggregates across 8 GPUs to write weights of 32 bits, which is FP32, the IOPS demands are extreme. EBS gets saturated and we hit OS level lockups. So our solution was to bypass block storage entirely. So we rerouted the Hugging Face cache and DeepSeek state into RAM disks. The entire checkpoint operation ran in volatile memory and safe tensors were piped directly to S3. Now, third is the LoRa configuration. Now, rank 128 targeting those four specific projection matrices gave the right balance of parameter efficiency and expressiveness for facial dynamics. So even with the fine-tuned model, we couldn't deploy 14 billion parameters for real-time inference. We need to perform distillation. So our pathway used adversarial diffusion distillation, which is called AD. So this 14 billion parameter model is the teacher. We trained a 2 billion parameter student diffusion transformer by matching feature maps between corresponding layers and using an adversarial discriminator loss to force the student's output to be indistinguishable from the teacher's. The key insight enabling aggressive distillation is the domain specificity. The teacher understands dogs, cars, landscapes, but we don't need any of that. We only need the facial manifold. So constraining distillation to avatar specific training data means we can compress far more than general purpose distillation would allow. And the result we got is a model from 50 denoising steps down to 2 to 4. That's a 12 to 25 times speed up in inference with minimal quality degradation on talking head generation. Now let me walk through the full end-to-end architecture. So this is where both phases come together. Phase 1 is the identity engine. This runs once offline per avatar. So we take 4K source footage through a data engineering module that produces structured tensors. Those feed into the identity overfitting engine, which fine tunes the model on that specific person's face. The output is the identity logged neural adapter, what we call the digital soul. Now, it's a LoRa encoding exactly one person's facial manifold. In parallel, we run knowledge distillation from the large foundation model, that is the teacher, down to a high throughput inference model, which is the student. Now, this is the add distillation process we just covered. Coming to phase 2, this is a runtime pipeline. Now, this fires on every video request. Text script and audio enter the orchestration layer, which fans out into two conditioning streams. Audio is encoded into audio embeddings, and motion intent is resolved through the geometric motion library into skeleton or pose data for the geometric guidance system. Both these streams converge on the generative core, which is our 8-step distilled inference engine, with the identity adapter from phase 1 injected here to anchor every frame to that specific person. So latent video flows through the identity consistency enforcer to correct drift, then the semantic audio-visual sync layer for lip alignment, and finally the 4K neural upscaler to produce broadcast-ready output. Let's look at the AWS architecture for inference. The full diagram is quite complex. We'll hit the 6 major layers. Okay, the first one is the front end, which is fully serverless. It is S3 static hosting behind CloudFront CDN. Layer 2 is a single API gateway REST endpoint. It routes job creation, avatar management, and status polling. Layer 3 is where the intelligence lives. Four Lambda functions. Lambda 1 is the preprocessor. It takes the input document, converts PDF or docs to text, chunks it, calls poly for TTS, creates the job record in DynamoDB, and invokes the wake Lambda. Lambda 2 wakes the EC2 instance, holds the health endpoint, and dispatches the job once ready. Lambda 3 is the avatar manager. It validates dimensions, generates a thumbnail, stores config to DynamoDB. Now, Lambda 4 is the status poller. The client polls this to get progress updates and the final video URL. Then comes the layer 4, the EC2 layer, which runs the GPU instance. This is where the actual diffusion runs. Layer 5 and 6 are the data layer. DynamoDB with 3 tables for system state, jobs, and avatars. S3 for storing all assets, and AWS Poly for TTS. Let's talk about the inference engineering challenges we faced and how we solved it. Nobody talks about it. The first one is the memory management. So at inference time, we're actually loading the primary model, the text encoder, audio encoder, spatial upscaler, and VAE, which accumulates over 45 GB of staged memory. Now our solution was a sidechain execution. A memory flush node fires in parallel with the latent data flow, clearing the diffusion model from VRAM right before decode begins. Now this makes the latent tensor untouched. Second one is the temporal consistency across 1440 frames. Diffusion models are probabilistic. The cascading chunk strategy addresses this, but the handoff frame selection is at 19-second, not 21. The model's coherent degrades in the final frames. Third is the upscaling decision. We evaluated AI super resolution post processing. It made the video look worse. The smoothing artifact was immediately visible, looks synthetic. So we rejected it entirely. Um, so what we did was a 72p spatial upscaling pass built into the diffusion pipeline, and this produced more natural results.
Traditional HR video production runs $3,000 to $15,000 per minute. Commercial AI APIs like agents or production costs, but replace it with $30 to $100 per minute, still unpayable at scale. Our pipeline produces a video at an order of magnitude below those commercial APIs cost. Fully automated text and branded video out. But the most important outcome isn't cost per video, it's reliability. The entire engineering effort, parameter locking, cascade chunking, handoff frame selection, memory management, was fundamentally about making the success rate high enough that the economics hold in production. A generation pipeline failing 40% of the time isn't cheap. It's infinitely expensive because you can't run it unsupervised. All right, so what's next? We have got two main things going on right now. First up, we are working on reducing 1 2 GB latency through distillation and keyframe caching, basically making it way faster. Second, we are wrapping up the ad student model training. Medium term, the big goal is real-time streaming avatars with sub 500 millisecond latency. So like half a second response time. To get there, we need digital model plus streaming way decode pipeline that replaces our current batch processing approach. And then we are starting to look at multi-avatar consistency. So maintaining a distinct stable identities for tons of avatars on single platform at scale. That's going to be next challenge. So here's the thing. The hard part really isn't generating the video anymore. The tech is there. What's actually challenging is making the results repeatable, predictable, and economically deployable at scale. So yeah, generating video is cool, but building a system that does it reliably at scale, that's where the real engineering happens.